Hello, my name is Isabella Zane. I'm a junior math and physics major at Texas A&M University. Today I'll be presenting my research of variance extrapolation in oscillator basis. So we want to solve the nuclear many-body problem. However, we can't solve this problem directly. So here we're going to be using a harmonic oscillator basis to approximate the solution. Now we cannot solve the harmonic oscillator basis in its full space because it's infinite, so we'll be solving in a truncated finite basis. Therefore, the accuracy of the approximation depends on the largest size of basis that we're able to compute. However, the problem is, if you look at this graph, for example, this is a basis size of 2, and for something like carbon, the dimension is 10 to the 4th, which is a very large thing to compute. And then if you increase the basis size a little bit to increase your accuracy, we're already at 10 to the 6th, which is a lot bigger. So what we're trying to do here is find a technique to improve the accuracy of our approximation without having to increase the size of basis that we have to compute. Here we're going to be using variance extrapolation. This method has been used successfully in condensed matter physics in the Monte Carlo shell model. And here we're going to be using it in the no, seeing if it can be accurately applied to the no-core shell model. But first, we're going to apply the problem in a Gaussian potential, which is somewhat of a toy problem. Because the harmonic oscillator basis with a Gaussian potential converges very quickly, we almost have an exact full space solution to compare our results using extrapolation with and see how effective this method is. So the extrapolation technique works because of some properties of variance. So if you calculate the variance of energy eigenvalues of different approximate eigenstates, it's going to be non-zero unless you're calculating in the same basis state. So if basically anytime you calculate the energy in the same basis, it's going to be 0 because it will be an eigenvalue of that basis. So here, for example, you have a basis size of 2, and the energy in the variance of the energy in this basis is going to be 0 because it's been calculated in the same basis. However, if you take this energy and embed it into a space of size 4, it's no longer an eigenvalue, so the variance is going to be larger than 0. So it also gives you a good gauge on how accurate the approximation is, because the closer the variance is to 0, the better the approximation is. So the closer your energy is to the eigenvalue of the full space. So you want to find a linear relationship between the variance and the energy. For example, if you want to calculate, let's say a basis size of 8 is a full space, and you want to approximate that because you can't calculate in the basis size of 8 for whatever reason. If you don't use extrapolation, the best estimate you have is the solution for your basis size of 6, which is not very good in a large scale sense. However, if you use variance extrapolation, so this point would be the energy from a base size of 4 embedded in a basis size of 8, and this point right here is the energy from basis size of 6 embedded in a basis size of 8. And if you form a linear relationship between these 2 points and find the y-intercept where it's at 0 variance, this will be your estimate for the solution in full space. So if you see here, oops, that's pretty accurate. But this isn't the only way you can extrapolate, because if you notice, there's a somewhat kink in the data right here, which is exacerbated in larger dimension sizes. So if you use alternating points, for example, you can use the energy from 2 and the energy from 6, both embedded in 8, from a linear relationship right here. It's still a lot better than not extrapolating at all. But yeah, right. As you can see, compared to the adjacent extrapolation, it's not as good, which is the reason why we use the Gaussian potential. So you can see which method is better in the long run before we put this technique into the full nuclear problem. So for example here, we're using our full space as a size of 20, because again, the Gaussian potential converges very quickly. So let's say 6 is the biggest basis you can calculate. If you don't do anything, this is your best approximation, which isn't very close. However, if you extrapolate, this is using alternating points, which, no, this is adjacent points. My bad. It's a little bit better than using alternating points, but both ultimately are better than not doing anything at all. So hopefully we can extrapolate. Oh, there's a pun. We can extrapolate from the results in the Gaussian potential and use some of the patterns we found in different methods and use it for light nuclei. And then we can compare it with real results